Welcome to Digital Signal Processing Lab, and today we are going to conduct another experiment. And the objective of this experiment is like this. Okay, so we have to generate and plot the following windows. Okay, so we come across in DSP number of times different kind of windows like rectangular window, Hanning window, Hamming window, Blackman window, and some other kind of windows. Okay, Bartlett window, or it may be a Kaiser windows. Okay, so normally these windows are useful in designing the FIR filters, right? So first we have to see how to generate this windows using the MATLAB. What will be its time domain waveform, and what kind of its frequency spectrum. Okay, what will be the frequency response of such windows, right? So we have to generate these windows, and we have to take this length of the window equals to 31, and even you can change this length and you can observe the effects of changing this window length, right? So here you can see this is the typical window waveforms, okay, in the time domain. So here you can see one thing, that this is the Hamming window, this solid line. Okay, so this particular curve is corresponding to your Hamming window. And remember that though it is plotted as a continuous curve, but normally in the window we will be getting a discrete sequence. Okay, so if you just sample this particular continuous waveform, you will be able to get the discrete sequences, right? So it is just like plotting the envelope. Okay, so you remember that it is not the exactly your window shape. Okay, the shape will be similar to this shown picture, but it will be discrete in nature. Okay, it will not be continuous curve, right? So here you can see this is Hamming window shape, and here you can see we mostly use the rectangular window. So rectangular window will have this particular shape. Okay, it will be having a rectangular shape. Similarly, we are having Hanning window, Blackman window, and Bartlett window. Okay, so these are the a little bit change in the shape you will be able to observe, right? So these windows are normally in any of the DSP book, you will find its mathematical expressions. Okay, so here you can see the mathematical expressions for rectangular window. So it is Wn. It will be defined equals to 1 when this n is in between 0 to capital M, right? So because we are choosing this window length of M plus 1 here. Okay, so n equals to 0 to capital M, this value will be 1, and then otherwise this value will be 0. Okay, so that you can also observe from this picture itself. Okay, this is our rectangular window, right? So if we sample this, okay, we are going to get the discrete sequence, and all the values of the sequences will be 1, right? Up to n equals to capital M, and n equals to capital n equals to 0. And less than that and above n equals to M, this Wn is going to be 0, right? So this is what we have written. Similarly, you can see this other windows like Bartlett window, mathematical expressions, Hamming window, Blackman window. Okay, so these are the different mathematical definitions, right? So if you wish to plot the time domain waveform of this window, what we can do is you can directly implement this mathematical expression onto the MATLAB. Okay, so you have to just write these expressions for this given limit of your time index n, right? So in this case here you can see this Wn is equals to 2n divided by capital M, where M is an even number, and here you can choose this particular definition of Wn when this n is in between 0 to capital M by 2. Okay, when it is greater than M by 2, that time we have to choose this particular definition to minus 2n by capital M. Okay, otherwise this window will be 0. So this way you can see we are having different windows, and we are having its different mathematical definitions, right? So here you can directly write these mathematical definitions, and you can get the corresponding time domain plot for your different windows. But normally in the MATLAB, we are having commands that can directly generate such windows. Okay, so we don't need to write this all mathematical functions, right? So that we will be look at when we go to the MATLAB. Okay, so normally after getting this windows, after generating such windows, we have to also get its frequency response, right? So what kind of frequency response this filter is going to give, right? So that you can normally you will have this kind of frequency responses, right? So this frequency responses corresponds to your rectangular window. So we know that when we are having a rectangular pulse, right? So normally the rectangular pulse will have its Fourier transform. If you calculate, it will be having a sinc function, right? So if you take the mod of that sinc function, you know that this portion is going like this in the negative direction. Again, it is positive direction. Again, it will be going in the negative direction. So if you take this mod, this all negative cycles will also become positive, right? So this way, you are going to get this type of frequency response, right? This will be your frequency response. So these are the portions where the zeros of this particular window functions exist, right? So normally this kind of frequency response we are expecting to get, and this particular frequency responses will be normally periodic in nature, okay, and it will be periodic by 2 pi. Okay, so after 2 pi, the same spectrum you are going to repeat, right? So you will be getting a periodic spectrum, right? So this type of spectrum typically in all the cases we are going to get with a little bit variations, right? So here we have to observe that here we have plotted the magnitude of your frequency response versus the digital frequency, right? So this is your magnitude of your absolute value of your frequency response, right? And then here is the frequency component. So here we can see, because when this frequency is small, okay, for the low frequency, this filtering operation is having certain gain, okay. So because it is having certain gain in this section, okay, it will be having its filtering action as a low pass filter, right? So it will be a low passing, it will be passing the low frequency component, but high frequency component will be attenuated, because gain offered by this filter is reducing when we are increasing the frequency. And as we know that the maximum frequency component in digital domain is pi. I have explained this fact a number of times in my previous lectures, okay. So here you can observe there are two important parameter that we have to observe in our Windows frequency response. The one is the main lobe width, okay. So here we will be calling this as a main lobe, right? It is having the maximum amplitude, okay, and then these will be called as the side lobe, okay. So this is your first side lobe, then it is second side lobe, and so on, right? So this is our main lobe, right? So here is the main lobe width, okay. So this is our main lobe width, including the negative frequency and the positive frequency, right? So here you can see this for the rectangular window, this approximate width of the main lobe is given by this particular equation, 4 pi divided by capital M plus 1. Similarly, in the other cases for other windows, this approximate width of main lobe is given by this corresponding equations, like 8 pi by capital M, okay, and 12 pi by capital M for Blackman window, right? So we are having different like width of main lobes, but it is important to note that this width of the main lobe is inversely proportional to the number of samples in the window, right? So if we increase the length of the window in number of samples, then this width will become narrower, right? And then here you can observe on the peak side lobe, okay. So this peak side lobe is also important, because here normally this particular width is offering you the pass band, and then these side lobes are giving you the attenuation, okay. So it will be acting as a stop band, right? So when it is in this stop band, the signal must be attenuated, right? And therefore this amplitude of the side lobe is also very important, okay. So here you can see this two columns, right? So here we have the approximate width of the main lobe, and here we have the side lobe amplitude. So you notice this written to be as a relative value. So it is written in the terms of what is the maximum amplitude at this point, and then relative to this point, what is the magnitude of this particular side lobe. Okay, so normally this is given in the dB. Okay, so we have to calculate this value into dB, right? Like here it is shown to be an absolute value. Okay, but we have to calculate this magnitude in dB, so we have to also take 20 log 10. Okay, and then we have to calculate this magnitude in dB, and then we have to give this relative magnitude. So if you see the typical frequency responses of the different windows, here it is for the rectangular and Bartlett window, you will be able to get this kind of frequency responses, right? So here we have this digital frequency up to pi, and then you will be getting, this is our main lobe. Okay, and then these are our side lobes, right? So these are our side lobes. So this will be our side lobe, and here it is main lobe. So we have to find it out, what is the width of your main lobe. Okay, and what will be the attenuation or amplitude of your side lobe. Okay, so that we have to identify in the case of various different windows, right? So here we can see this typical curves for Bartlett window, for Hanning window, for Hamming window. Okay, so this kind of result or response we are expecting when we will be getting the frequency response for such windows. Okay, so we'll try to see this. Okay, and here you can obviously observe that in all these four pictures, you can see somewhere we are having the main lobe width is small. Okay, somewhere it is large. Okay, these attenuations are different. Okay, so that you can also observe from this table itself. Okay, because it is depending on this particular expressions. Okay, and based on this expression, this main lobe width will be decided, and also this side lobe peak is going to be decided based on this particular windows. Okay, so let me go to this MATLAB. Okay, we'll try to implement this. Okay, and we will be trying to verifying this particular frequency responses, right? So here I have written the code for this window. Okay, so let me explain you what is this window and how to write this code. So here I have written this code. Okay, so the first line is clear in CLC. I have already explained this is to clear the variable in the previous variable in the workspace and to clear the command window screen. Okay, so here we have to take the window length. So we have to give the window length here, and then we have to first define the time index array, right? And then for the rectangular window, in the command, in the MATLAB, we are having this boxcar command. Okay, so just we have to write the boxcar command. And instead of writing any mathematical expressions, we can directly write the boxcar command. And here we have to give this size of this particular window, right? So because the size we have saved in the variable m, so this m we have to substitute here, right? So boxcar m, if you give, then it will be generating a particular window, and that discrete sequences will be stored in the variable WR. Okay. Similarly, we have to plot this WR by using the stem functions. So we have to use this time index n that we have generated, and then we have to write this WR, and we have to get the discrete plot, right? And now again we have to, because we have to got the frequency response, I will be using this frequency Z command. Okay, so I have already explained this frequency Z command. So here we have to give this sequence that for which we want to calculate the discrete Fourier transform. Okay, and then we have to write this number to be equals to 1, and this should be 512 to get the this frequency response for a equally spaced 512 discrete frequency points. Okay, so this pi will be divided by 512, and for those 512 equidistance point, we have to calculate the frequency response. So this frequency response and corresponding frequency variable will be saved into W1. Okay, so this will be our frequency response value, and this value will be the corresponding frequency which is going to be saved. And then we have to plot the frequency response. So to plot the frequency response, we have to use this plot command. And here I'm just normalizing the frequency. Okay, as we know that this frequency W1 will be going from 0 to pi, but here I will be just normalizing this W1 with respect to pi. So you will be able to see that this x-axis is going to vary from 0 to 1 because we are normalizing it with respect to pi. Okay, and here, because we have to plot the this amplitude response in terms of dB, so I have taken the absolute value of this frequency response frequency WR. Okay, and then first we have to calculate the absolute value by writing this ABS command, and then again we have to take this 20 log 10. Okay, so it will be giving you amplitude in dB, right? So we have just converted it into dB, and then we have to use the grid if you want, and then we can see the frequency response. So here you can see I have written the code for other windows also. Okay, for rectangular window we have to use the boxer command. A similar code you can also write for Hanning window. Just you have to write Hanning instead of writing the boxer. Okay, so we can directly write Hanning, and if you wish to get the Hamming, here you have to just write the Hamming window. Okay, so if you write in this way, you will be able to get this responses, right? So this way, we have to write this code, and then we have to observe the outputs, right? So I have just shown this 3 windows, okay, that we can observe here. So if we execute here, okay, we have to give the length of the window. So I will be giving you 31 here, okay. So if we write 31, then here we can get this plot, okay. So here we are getting 6 different plots. Okay, so I will be showing you one by one. So you see figure number 1 and figure number 2. So this figure number 1 is showing you the waveform of your rectangular window in time domain. Okay, so as we know that in the rectangular window, all these values to be 1. Okay, from n equals to 0 to capital M, right? So here we have given this, and the size of the window is 31. Okay, so this last value of n should be equals to 30. So here we are going to get this once for 31 times, right? So it will be going from 0 to 30. So this is the time domain waveform of a rectangular window, and here we can see this frequency response curve of our rectangular window that we have obtained. So you try to see this waveform. Okay, this is our digital frequency, because I said that it is normalized with respect to pi. So we are getting this frequency from 0 to 1, right? So here you can see what is the maximum value. Okay, so that we have to observe, and we have to also observe what is the main lobe width. So here you can see, as I said, that if you make this comparison with respect to this table, you can see for the rectangular window, okay, this approximate width of main lobe is 4 pi divided by m plus 1. So you can see that because this 4 pi divided by m plus 1 is also considering the negative part of our frequency. Okay, but here when we see this window width, we will be only able to observe this portion, only the positive frequency portion, right? So if you see what should be the this particular point, okay, it is 2 pi divided by m plus 1. So because it is normalized with respect to pi, you can divide it. So you will be getting this point equals to 2 divided by m plus 1. So you just try to do this small calculation. If you do 2 divided by m plus 1, because capital M we have taken equals to 31, so it will be 2 divided by 32. So this result will be coming out as 0.0625. Okay, so 0.0265. So here we can see the same thing, that in this case, this frequency value, okay, this particular frequency should be near about 0.0625. Okay, so here we can see that this value is coming out as 0.064. Okay, so around 0.0625 it should coming means it should be the width of that particular main lobe, right? So here that frequency you can observe, right? At this particular frequency, this 0 is coming. okay, this particular 0, right? So here is the main lobe width that we are going to get, okay? So if you double this particular value, okay, you will be able to calculate the main lobe width in considering both the positive and the negative part, right? So this is what is our main lobe width, right? So now again, you can see this second column, okay? What is the second column? We have to see this relative amplitude of your side lobe, okay? So here you can see this side lobe, okay? So this is our side lobe, and here we can make a relative measurement. So if you take this particular point, okay, if you take this particular point, let me go here, okay? So if we take this particular point, then you can observe this particular magnitude, okay? At x equals to 0, this magnitude is around 29.82 dB, okay? So now again, you can take this particular magnitude, okay? So if you take this magnitude, okay, of the side lobe, here you can observe this magnitude is around 16.6 dB. So if you subtract 29.8 minus 16.6, this relatively it is lesser than this particular magnitude by minus 13 dB. Okay, so the same thing is written here. Okay, it is minus 13 dB, right? So this way we can able to observe this particular curve. Okay, this particular frequency response. So there's two things we have to observe in all the different cases. So here you can see this is for your rectangular window, okay? Now you can again see the other windows that we have generated. So this window is your Hanning window, okay? So this window is our Hanning window. So this Hanning window we can see, okay? It is a discrete sequence. And I also shown you in this picture, okay? So here you can see this particular Hanning window. So this dotted line, right? So this line is corresponding to your Hanning window, okay? So we are going to get the similar shape, but you remember that the shape will be similar to that, but it will be a discrete sequence, right? So this is our Hanning window in your time waveform, okay, time domain waveform. And now we can also see its frequency response, okay? So here is the frequency response of our Hanning window. Okay, so here we can see this, the width of this Hanning window has changed now. Okay, so this major lobe width is changed. So here you can observe one thing, this width for Hanning window. If you see from this table, for the Hanning window, this width is given by 8 pi by capital M, right? So if you see only this point is going to become 4 pi divided by capital M. So because it is normalized with respect to pi, it will become 4 divided by capital M. So if you divide 4 with capital M, here the capital M is equals to 31, then this value is coming out to be 0.129. You can do this simple calculation, please, okay? So it will be 4 divided by M. So here capital M is equals to 31. So that you can divide, and again note down this point, right? This point, okay? So here if you observe this particular point, okay, so let me go to this data tips, and then we can observe this point, okay? So if we go to this point, and then if we try to see this data point, okay, here you can see this point is coming out to be around 0.125, okay? So exactly at 0.129, because we are taking the discrete values of omega. Okay, so it should be around 0.129. So it is coming around 0.125 in this particular graph. Okay, so this is the major lobe width that we are getting. Okay, if you double it, you will be also including the negative frequency part. Okay, one more thing that we have to observe, obviously, about its magnitude, okay, the side lobe amplitude. So you can observe when your omega is equals to 0, here you can observe its magnitude, okay? So this magnitude is 24 dB right now, okay? So if we take this magnitude over here, okay, 24 dB there, and this is our side lobe, first side lobe, okay? So at this point, you can see this magnitude is around minus 7.5 dB, okay? So there it was 24, and here it is minus 7.5. So it is almost 31 dB. Okay, it is minus 31 dB with respect to this particular point. So that you can also observe from this table. It is minus 31 dB, right? So it is relatively minus 31 dB from its peak value. Okay. So this way you can make this observation. So while telling this rectangular window, you remember I said that we have to divide 2 divided by 32. You remember we have taken m equals to 31. Okay. So the size of the window is 31. So you will be getting 2 divided by 31. If you do this calculation, will be giving you 0.0645. Okay. So this is the point that we got. Okay. So that time I was saying it's 2 divided by 32, but it is not 32. It should be 31 because we have chosen the window length equals to 31. Right. Similarly, here in this case, again, it will be 4 divided by 31. It is not 32, remember. Okay. So that's why here we can see this point that I have just shown you, this particular point. Okay. So this value is coming around 0.125. Okay. So this way you can observe all other windows, right? We can also see this is our Hamming window. Okay. A little bit variation in this graph you will be able to observe if you compare with the Hamming window. And then this is our frequency response curve. Okay, this is our frequency response curve. So this is corresponding to your Hamming window. A similar graph I also shown you in this slide. Okay, so this is our Hamming window. Okay, here you can see this Hamming window. A similar graph we are also getting in this case by using the MATLAB. So you try to again verify what is the major lobe width and what is the side lobe amplitude. Okay, so I will be stopping here. Okay, so you try to get the other windows also. Okay, for example, in MATLAB I have written this code. Okay, so you can also try to generate the Blackman window. So for this you can use this Blackman command. Okay, similarly you can also generate the Bartlett window. Okay, so try to do that and try to verify this table. Okay, you try to verify this table. You have to verify these two columns, right? So I stop here. Okay, so if you have any doubt, let me know with your comments. So thank you for watching this video and stay connected with the channel. Thank you.